chemistry, those make up the last 20% combined, or thereabouts approximately. And many of those things we will have already talked about. So we're going to spend the majority of our time on the first two topics, and then we will point out similarities and whatnot in the minor topics and the approach to take for those minor topics. We will have a couple of breaks like we did yesterday, one after engineering and one after economic. And LESAT Ridge Review for study partner or attendance certificate. We don't offer any guarantees. As a reminder, you still have to study after you're done with this. So if you're taking the exam in October, at this point, you will need to devote every waking hour that that's not at work to your studying process, or you're not going to be able to manage to get it done. There's no more weekends between now and October. If you're taking the March exam, congratulations, you're doing this the right way and getting started really early, which is awesome. Again, if you have audio problems for some reason, just go ahead and close your program and then sign back in again. And you shouldn't miss too much in doing that, but that usually fixes the problem. So our first topic today is going to be engineering geology. And this is my favorite topic. This is what I practiced most of my working in consulting career. And so the topic here is on the PG, it's 19%. If we combine that, that's going to be 14%. What that is about 15 questions on the FG and 21 questions on the PG to make up that percentage. And it covers things like geologic hazards. And when you're looking at the geologic hazards, you have to do landform analysis. You have to identify them from maps or photographs. You need to evaluate the hazards, including mitigation and risk analysis. Lab and field tests don't count towards your experience to taking the exam, but they do have questions on this. So those of you that are in the environmental field, which is more than half of you, you may not have any experience with this in the engineering geology. So we're going to talk about this a little bit, point out some of the important things to know for that, so that when those few questions come around, you've got at least a little bit of exposure to it. And the last piece there, site investigation methods, tools, and applications, we already talked about this. This was what we did yesterday morning with the general and field. So here's a big overlap right from the beginning here on that. Now, part of what you need to know in any of the fields of geology is something about the language and what the terms mean. So our first question in the engineering section of the practice questions is on page 15 in the practice questions section of your course notes. And what we have is a bridge where we are concerned about the abutments. And it talks about abutments in terms of right and left. We usually think about directional information being given in north, south, east, or west. But in this case, they use the right abutment or the left abutment. And how do we know which is which? You have to stand looking downstream, and if it's on the right side, then it's the right abutment, and if it's on the left side, it's the left abutment. So that's part of the language that you have to know. And the other part is PI. What's PI? That's plasticity index. And for the purposes of this question, I'm just going to tell you that a PI of 35 is prone to swell, which means it's prone to slide. And I'll talk about PI more in a minute, but for this, we'll just take that 35 is a prone to slide material. So when we put a strike and dip symbol on the right abutment, it's dipping into the stream. So it's a dip slope. And those are the ones that are going to be most likely to slide, particularly when you have high PI levels. And if we take that same strike and dip symbol and put it on the other side of the stream, it's dipping into the hill. And in order to slide, it would have to move the whole hill. And that is an unlikely scenario, highly unlikely scenario. So just understanding the language here was a big thing. Most geologists are aware that in general geology terms, if you have a dip slope and you have a slide prone material, then it's going to slide much more easily than it would if it's dipping into the slope. So that part's just kind of general geology. Okay, then a couple of you indicated that you weren't totally comfortable with the Unified Soil Classification System, so let me do just a quick rundown. You don't need to know all the details of this. You don't need to know the percentages, but if you note this symbols column, they will use these symbols on at least a dozen questions on each exam. And it's not just engineering geology questions that they will use them on. They'll use them to describe soils for hydro questions and such. Stratton said. So you need to know what these symbols mean. If we break these soils down, we've got the coarse grain soils, which is the upper half, and the fine grain soils, which is the lower half here. The coarse grain soils are going to be the gravels and the sands. The first letter of the gravels is G and the first letter of the sands is S. And so on your symbols, the first letter is going to be G and S respectively. Then we've got modifiers, and the modifiers depend on whether or not you have fines and how the gravels, when they don't have fines, how they're graded. So as geologists, we learn sorting. As engineers, they use the term grading. Grading and sorting are opposite. So well graded is poorly sorted. That means that there's a little bit of everything. Well graded has a W, so GW and SW are well graded sands and gravels. GP is poorly graded, which means that it's well sorted, like a beach sand or something like that. So in this case gravel, this SP would be more like a beach sand. So P is poorly graded, meaning that there's very few grain sizes present. And then for the gravels and sands with fines, they use M for silt and they use C for clay. So when we get down to the fine grain soils, the M and the C, those are the silts and the clays, that is the first letter of the symbols. O is for organic. They're probably not going to ask about organic soils because there's not that many of them in the country. So M is silt and C is clay, and now the modifier is L or H. L means low plastic, H means high plastic, and we'll talk about plasticity a little bit more as we go along. But that's pretty much all you need to know about this. But be aware that there's going to be at least a dozen questions on the exam that include these symbols to describe materials, and that grading and sorting are opposites. So if you have a classic geologic education, you will have learned sorting. If you have taken an engineering class, then you will understand the grading more. So just pay attention there. It's quite simple. It's just a matter of making sure that you're comfortable with it. Okay, so swelling is a problem. Whenever we're working with engineering geology, it usually has to do with some sort of an engineered structure: tunnels, dams, high-rise buildings, housing developments, road cuts, I don't know, bridges. And we get involved in those kinds of investigations to make sure that the geologic aspects are taken into consideration when they are working through the engineering for it. So swelling potential is a problem. Swelling causes damage to lots and lots of properties. So some of the things that we have to think about when we're thinking about whether or not something has swelling potential: plasticity index is one. I'll talk more about that later. Clay mineral type is one. Some swell, some don't. I'll talk more about that in a minute as well. Clay content. If it's all clay, it's going to have a higher swelling potential than it is if it is half clay and half sand. The sand will replace the clay, making it so that there's not so much swelling. The pore fluids. Fresh water will enhance swelling potential in clays. If you have some other component in there like chlorides, like the calcium chloride and potassium chloride that I talked about yesterday for drilling muds, modifying drilling muds if you have swelling potential, that will reduce the swelling potential. How close is it to the surface? Some places it doesn't matter. Where it's humid and it rains a lot and the ground is always damp and wet, then it's not going to matter because the soils are always going to be swollen. So it's the shrink swell from the expansion and contraction of the subsurface materials that causes the damage. So in arid environments where we don't get rain for months, and then when it does rain, we get a deluge, and that saturates the ground and it swells all up, and then it dries out and shrinks back down again. It wreaks havoc on engineered structures. So the closer it is to the surface in these arid environments, the more likely you are to have a problem. But in humid, it's not so much. Temperature, same sort of thing. Part of the country freezes repeatedly during the wintertime. And the clay holds the water in its non-interconnected pore spaces. And so when it freezes, it will expand. And this often causes heaving in roadways, for example. I used to live in New Hampshire, and the roads, every springtime when it started to thaw out, and it would freeze and thaw a couple times a day, depending on the shadows and the air temperature, they would have big signs saying frost heaves. And we had a joke where frost heaves must be running for city office again. But that was related to the temperature because it would freeze and thaw multiple times during a day. So here we go. Plasticity index. PI, this is an acronym that they will use. They probably won't say plasticity index, they'll probably say PI. Well, the plasticity index is equal to the liquid limit minus the plastic limit. What are those limits and how do we get at them? The plastic limit, if you take a pad of soil and put it in the palm of your hand and roll it out to make it a worm, as long as it's a worm, it's exhibiting plastic behavior. And if you keep rolling it out and it dries out and falls apart, that's the point when you have crossed from plastic behavior to non-plastic behavior. So for plastic limit, we are going from wet to dry. And once you've crossed that threshold, once your worm breaks up, then you weigh it and dry it and weigh it again to get the moisture content, and that's your plastic limit. The liquid limit is obtained by going from dry to wet. And what we do is we do an Atterberg limits test, which is you use this device, which is called the Casa Grande cup. And the Atterberg limits test then involves putting the pad of soil in there, using this device that's lying down here on the table with a point on it to make a groove down the middle of your soil sample in the cup. And then you turn that handle and it has a point where it raises up for a bit and then there's a gap, so it drops and it thunks onto the block. So it's jarring. And if you turn that 25 times, you've reached your liquid limit when that closes. So odds are you're going to start out and you're going to do it, you're going to turn it and nothing happens. So you have to add a little bit more water to it and mix it all up and then put it back in, make a new groove, turn the handle, nothing still happens. So then you go to add a little bit more water, and at the point at which you get that gap to close within those 25 blows, you have crossed the liquid limit. So we're going from dry to wet here. And once you've crossed that liquid limit, you take the soil and you weigh it and dry it and weigh it again to get the moisture content at the liquid limit at that point where it closes. So now we've got two water contents, the plastic limit and the liquid limit. and you subtract the plastic limit from the liquid limit, and you get the plasticity index. So in our table, you can see that anything that has a PI of less than 15, probably nothing's going to happen. The swell potential is very low. Anything greater than 30, you can pretty much guarantee that you're going to have problems with shrink swell. It's nice that those are multipliers of one another because it helps you to remember that value. So 15 and 30 are important here. In between 15 and 30, for the moderate shrink swell potential, maybe you'll have problems, maybe you won't. So it just depends on what the situation is, and maybe the slide that we just looked at, what other factors are in play here as to whether or not you're going to have potential swelling in that moderate range. So 15 below, no problems. 30 above, lots of problems. And then swelling potential by clay mineral type. And you're going to look at this table and go, oh my God, there's a lot of minerals I have to memorize. And when you're thinking about the minerals that you want to memorize, there are something like 4,000 minerals. I don't remember exactly how many, but there's a lot of them, and you don't need to know those. What I would focus on is those that are going to cause problems. So when we look at the kaolinite group here, we've got 4 minerals. Don't worry about them. Don't look at them. Don't memorize them. Don't even think about them. Same with the illite group, because the swelling potential for both of those is low. The illite group has another 6. So forget those as well. The ones we need to focus on are the smectite group. And they will use the term smectites. They will use some of those minerals, because if they give you a mineral that you recognize, there's probably a problem with it. And if you don't recognize it, don't worry about it. So montmorillonite and bentonite are the most common of the smectite group minerals. And then that just leaves, which most people are familiar with, and then that just leaves 4 others that if you don't necessarily memorize them, but just know that you have seen them and they pop up, it'll come back to your head. Then vermiculites, they have moderate shrink swell potential, but they are very slow to respond. So I wouldn't worry about those. There also isn't very many of them, so I wouldn't worry about that. So focus on those smectites and know the term smectite, because that often shows up on the exam. For grouting, you don't need to know all the you don't need to resolve chemical equations or whatever for grouting. The basics is what you want to know. And we'll go through some of this and the importance of some of this, but for more information, if you want to read up more on it, these 5 links are both on our webpage, but some of them are also, well, you can see them in your course notes on the slide. So these are a place that you can go to get more information if you need more. And it's not that you need to resolve the chemical equations, but you should know what's going to happen. So we're going to go through that. So what are you going to use grout for? And what is the grouting technique that you're going to use to accomplish that? If you have differentially settling structures of some sort, then you're going to want to lift and level that structure. And in the process, you're going to want to stabilize the subsurface materials. So you're going to use consolidation grouting and compaction grouting to do this. And how that works is that you inject grout into the ground. Part of it glues it together, but part of it also, because you're injecting into something that's already full, it's going to expand into spaces and provide some uplift pressures so that you can level up your house again, or whatever building. And the engineers usually design this stuff, but making sure that you know what to recommend. Preventing contaminant migration. Most contaminant migration is horizontal. So it's following the groundwater gradient. And so in order to stop something that's moving horizontal, you have to build a curtain or wall to stop it. So curtain grout is a series of boreholes where you you calculate the permeability of the soils, and then you grout these holes in a particular order. So first of all, you put in the primary ones, and then in between those, you put in the secondary ones, and then in between those, you put in the tertiary ones, in between the secondary and the primary. And then you do a second row. And if you need to, you can do a third row. And the second row is all halfway in between. This diagram doesn't show that very well, but this first one does. It's halfway in between the primary and tertiary, so that you're closing up those spaces to create a wall, an impermeable wall. Eliminating or reducing subsurface seepage. How many dams have been built that don't hold water? Well, to be honest, all of them. But what happens is oftentimes when people are putting in dams, they're really concerned with the dam embankment area. And they forget that there's going to be 100 feet ahead on the entire valley bottom upstream of the dam. And is that 100 feet ahead going to impact anything that is underneath the ground? So if you have a permeable bed, then, sorry, there's a question here. Let me finish this first. If you have a permeable bed and you put 100 feet of head on it that's running underneath the reservoir, you're going to have a waterfall downstream where that formation daylights somewhere. Because it's so permeable, it's going to be flowing out of the reservoir and following that bed wherever it goes. And if it daylights, you're going to get water. And so if you're doing that, that's something you should find before you put the dam in, but people often don't. And so then you got to go back and lower the water down and put in what's called a blanket grout. And the blanket grout is basically a whole series of boreholes in a grid pattern, closely spaced, shallow, to create a blanket over that permeable bed. Hopefully you'll stop it, but probably you will only slow that seepage down. The question says, why are the ranges in plasticity index and not plastic limit? I don't know that. So Patty may be able to find something on that while we're talking, but they've always used plasticity index, which is a relationship between the liquid limit and the plastic limit. And those limits will change depending on the material. And so something that might have a high liquid limit may not have a high plastic limit. And so you have to relate those two together to be able to get the plasticity index.
Yeah, I think what the range is important rather than just one value of plasticity.
Okay. The other thing is securing abandoned wells. And we have rules about this now. There didn't used to be. When I first started practicing geology, you could just fill up a hole when you were done drilling it. And now you have to seal the holes and all that sort of stuff. And this is especially important if you get down to water, or you get down to ground that sometimes has water. So the highest groundwater level, which can be evidenced in soil samples that come out. And it's doubly important if you're going through an impermeable bed into a confined aquifer. So local rules apply for sealing these up so that you can protect the water that we still have that is good. Then there's eliminating voids. And in the southeast part of the United States and Missouri area, there are sinkholes. And this happens because the limestone dissolves, and we'll talk about this a little bit more in the geomorphology section later on, but the limestone dissolves in the presence of groundwater, particularly at the water table. And so the void spaces can sometimes collapse, causing sinkholes at the surface, which will cause damage to any structures or even just the ground surface that is above it. So you need to grout up those holes. And these void spaces can also be abandoned mines. So here in Colorado, we have a lot of underground mines looking for gold and such, and coal. And actually, the town that I live in, Lafayette, we had a sinkhole where a mine tunnel collapsed underneath one of the city roads. Thankfully, it wasn't under a house. So you can do, depending on how good access you have, you can either just grout them up like is shown in this picture, or you can, if it's you have exposure to the surface of part of it, then you can put old waste rock, or they used waste concrete from old sidewalks that they'd had to take out because they'd gotten broken up. And those went, that filled in the hole, and then they and then they grouted around it. So that's cavity grouting, and there's a special kind of cavity grouting called contact grouting. And this is where, for example, if you have a tunnel lining, the tunnel lining for strength has to be in contact with the wall rock. And if it's not in contact with the wall rock, the lining is going to be weak. So if you fill that tunnel up with water, for example, for a water transport tunnel, the water weighs a lot, there's a lot of pressure behind it, and it will cause that to break and wash out and create lots of problems. So you want to fill in those void spaces. So in this diagram, we have our tunnel, but we have void spaces behind. You can see these hatchet areas. And those can occur during construction. Things weren't taken care of properly. They can occur in limestone terrain if you have water seeping alongside the tunnel lining. It can dissolve the limestone over time, making void spaces. It can occur where you have piping problems. What's piping? Piping is where we have a little bit of water come in to space, and it takes away a few little grains of soil. And then that leaves a bigger space, which allows more water to go in, which allows more soil to be removed. The more water gets in there, the bigger the grains that can be carried, because the water travels faster, which allows it, that increase in activity allows it to carry away bigger particles. So you can develop pores, void spaces in no time. The Teton Dam actually failed because of piping, and it failed in one day. One day the whole thing was gone. So this void space back here needs to be filled in. And a lot of times what they'll do is they'll go in and they'll x-ray the tunnel and find out where these void spaces are, and then you just drill a little hole through and pump some grout in there to make it be in contact with the tunnel lining. What's a pumpable grout mix? Well, what the drillers consider to be a pumpable grout mix and what the specifications call for are usually two different things. So this first mix of 5.2 gallons per sack of cement is the minimum that can be used. It's pretty thick. Drillers don't like that. So if you turn your back or go away, they're going to add more water. What happens when you add too much water to grout? It shrinks. When it shrinks, it cracks. When it cracks, it leaks. So this is what a shrinkage crack looks like. And you can tell it's a shrinkage crack and not a structural crack. For one thing, it's vertical. Most structural cracks are like 45 degrees, but not always. But the other thing is that one side matches the other side exactly. So we've got a little bump here, it tucks into that little dent there. This bump here tucks into this dent, and they just move laterally as opposed to at an angle, which is what you would get with structural cracks. So you can make another mix that makes the drillers a whole lot happier, and that's where you add 20% more water. That's the second mix listed there. 20% more water and only about 5% more solids. The solids that you're adding are bentonite. So when you shear that in really well to the grout, it reduces shrinkage potential. And so even though you've added more water to make it the drillers happier, it's not likely to shrink because of the bentonite that's been added. Decomposition is another problem that you can get with grouting, and this is as a result of sulfate minerals, the presence of sulfate minerals. When sulfate minerals are present and you have groundwater present, the groundwater creates sulfuric acid, which dissolves the cement. So what you get is a foundation that you pour that looks like the one on the left here. And then with groundwater being present, if you have sulfate minerals in your cement or concrete, then all that is left over time is just the aggregate here because it's dissolved the cement part out. So here's some more minerals that you should be familiar with because these are troublesome minerals as well. Gypsum, barite, and anhydrite are the most common of these sulfate minerals. And then we've got 6 others here that are sulfate minerals as well, but they're a little bit less common. So now we've covered half of the minerals that you need to know something about for the mineralogy section. That's our last topic. So familiarize yourself with these a little bit so you know you're at least familiar with the names. Okay, concrete aggregate. The strength between the aggregate and the cement. Concrete is composed of aggregate and cement. The strength that you have that is for the concrete is based on the bond between the aggregate and the cement. And so if your aggregate isn't any good, or it's reactive, it's not strong enough, all these things are going to cause problems because it will compromise the bond between the cement and the aggregate. So aggregate strength, there's a test called the LA Rattler test or the abrasion test. It's this big device. It's really just a big tumbler. And if you find a rock that you think you want to use for aggregate, you weigh it and you measure it and you throw it in the tumbler. And then you add these little balls. They're steel balls. They're called charges. You add those balls and you tumble it around for a while. If you got nothing but powder when you're done, I wouldn't use that because it's not strong enough. It's going to break up inside the void space that it occupies, and you will have no bond between the cement and the aggregate. If it's still pretty much intact, then it's going to be good stuff. So the aggregate cement mix is dependent upon what it is that you're building. You know, roadways have different cement aggregate mix than patios or pool decks or retaining walls. So you just have to figure out exactly what the right thing is for the structure that you're building. The composition of this aggregate, sometimes materials with low specific gravity, this is high porosity, can be problems. This is because the high porosity materials may have water held in the pore spaces, and if you live in an area that freezes, then that water that's in the pore spaces are going to expand and it's going to break your rock apart, and the aggregate itself will be breaking up inside the cement space that it occupies, and so you lose that bond. Weak materials, already talked about that test. Some of the materials with water-based silicas or carbonates, these are reactive. And what happens when you have reactive materials is that you get a gel forming. And you don't need to know what the chemistry is that causes it, just know that this happens. So this is, you're looking at the aggregate within cement. This light gray stuff is your cement and the dark gray stuff is the aggregate that's in here. And this is reactive. So what's happening is that this black space is a gel that develops inside the cement. And then it's like having a ceramic bowl with jello in it, and you put a rock in the jello, and then you call that concrete. Well, it's not. You don't have any bond between the aggregate and the cement, then you've lost that bond. This happens over time, so it's not immediate, but it is a very distinct problem that you don't want to have. So you want to make sure that you get aggregate composition that is good, that is non-reactive. What are the water-based silicas? Things like cryptocrystalline quartz or chert, some of the volcanic ash glasses. Those are going to be problems. Carbonates like dolomitic limestone will react as well. So materials with sulfates also are going to be a problem. And this is what I was talking about earlier. Here's a good example of it. This isn't underground, but this is a bridge support. And rain is a little bit acidic. And when it percolates down through organic materials, it becomes a little bit more acidic. So when it enters the streams, it's a little more acidic than it is when it comes out of the sky. And you can see that the cement has been dissolved here. And what's left, all this bumpy stuff, is the aggregate that's there. And that's not this isn't an example of the aggregate itself causing problems, but the stream being acidic is dissolving that. And that will happen if you have groundwater that's acidic also to dissolve the cement part of the concrete. Can you mitigate these? Yeah. The cheapest thing is to find a non-reactive aggregate, and the engineering geologists are often hired at the beginning of a project to find sources for aggregate that are appropriate for what it is that you are going to be dealing with. So one thing that they will sometimes ask about is what are non-geologic considerations that you would have to take for a particular project. And transportation is one of those. So if you're hauling dirt for a project or rock or whatever, if you have to go a long ways away to get the materials that you need, then the transportation costs are going to be outrageously expensive. So that's one thing that's important about finding aggregate sources near your project because of the transportation costs. You can change the alkali content of the cement to change the overall for the concrete. You can do this by using some supplementary cementing materials, fly ash, for example. If you take that and grind it all up. Patty's going to talk about this a little bit in the economic, because that's where it comes from, burning coal. So if you live in a community that has a coal burning power plant, then you might have access to fly ash. But if you live in California where they don't have any of those, for example, or Washington State or whatever, you can't use it because the transportation expenses are going to be too expensive. Same thing, ground up blast furnace slag. You mix that into the cement and it will change the chemistry. Pittsburgh is a good place to get that stuff. So lithium compounds, these sound expensive because they are, lithium is using the element name, and that always sounds expensive to me. So that's a solution, but it's an expensive one. And then a very inexpensive one, if you have access to natural pozzolans. The silicious or silicious aluminous materials is what make up natural pozzolans. And when you mix those with calcium hydroxide, it makes a very strong, or strengthens, cement that you have. So it will be stronger. It takes a little longer to get permanently strong. It's a relatively slow process, but it is stronger and better when it's all said and done. And they actually used these in Haiti, and probably will do it again after the earthquake that we had this week. But in Haiti, with the big earthquake that they had, I forget what year it was, quite a few years ago at this point, but they used natural pozzolans because they had siliceous aluminous, naturally occurring siliceous aluminous materials that they could use, and they didn't have non-reactive aggregates. Okay, bad news. They sometimes use the ASTM standard number to talk about a particular lab test. And I hate that, because if you are going to be taking the time to do lab tests in the lab, which your experience, it's cookbook, so your experience doesn't count towards the practice exam. If you are spending too much time working in the lab, because you're not making judgment calls, you are doing exactly as you're told from the specifications. So you're going to look it up. And the geologists don't do these anyway, but sometimes they do give you the ASTM standard number. So let me give you a help to understand what this number means. You have a letter to start with. That letter probably is going to be either C, D, or E for the exam. C is a cementatious test. So this would be testing things for cement, like the Ehlers-Rattler test or abrasion test. This is a C test because it's testing for cement. D, they call the heading for this category is miscellaneous materials and products. But if you just call D dirt, these are all the soil tests. So here's our Atterberg limits, sieve analysis, hydrometer. These are all soil tests because of that letter. E, the heading is miscellaneous subjects, but if you call that environmental, then all the environmental tests are under the E category. So that helps a little bit in trying to figure out what this is. G is degradation, and they haven't had any of those yet, but I just thought I'd put this up here so that you're familiar. So that's the first number. The second number is the number of the test itself. And then the hyphen and the number that's after the hyphen, that's the year that this test was made. And sometimes they change them a little bit, so they'll upgrade the number. So like the Atterberg limits test, I was doing these back in the 80s, 70s, and 80s. And the most recent version is 2010. So they'll modify it just a little bit sometimes, and then they change the date. So this is 2010, this is 2004, and this is 1963. So that's what those numbers mean. And I'm sorry that they do this to you because it hardly seems fair. But the Atterberg limits test, I already talked about that. Sieve analysis, this is where you take the soil and you dry it out, and then you put it into a stack of sieves with the big holes at the top and the small holes at the bottom. And then you put it on a shaker table and you shake it around for a while, and then you weigh what's on each sieve. You guys all probably did one of these in college, and then if you aren't working in engineering geology, haven't done any since. So the silts and clays all end up in the pan below because the 200 sieve, the silts and clays all pass through the 200 sieve. So the 200 sieve and up covers the other grain sizes. And I'll show you a gradation curve in a minute. The hydrometer then tests the silts and clays. And what you do is you put your soil, everything in the minus number 200 sieve pan, you put that into a graduated cylinder with anti-flocculating agents so that the clay particles will let go of one another. And then you mix it up. I always used a milkshake machine to get it all mixed up. And then the hydrometer is actually this little device that floats in here. It's got a bulb at the bottom, and it just floats in the middle of the graduated cylinder. And when this is just distilled water, then it's at the top of up here. Excuse me. This thing measures specific gravity. So when all the other soil is floating around in there, the silts and clays are floating around in there, the specific gravity is higher than it is when it's just clean distilled water. And so you watch it over time. And if there's any sand left in it after about a minute, the sand is all at the bottom. And so that hydrometer will drop down. After about 12 hours, the silt is all out. And the only thing that is remaining in suspension and can remain in suspension for a very long period of time are the clay particles. So this is how we distinguish between the silts and the clays. And you can see the hydrometer floats a whole lot higher when it's got all this other material in it, the silts in here. And then after they drop out, the specific gravity of the water drops, and so our little device drops down and floats a little lower. Compression tests. Mostly the engineers do these. I have been known to do a number of unconfined compression tests out in the field. When I was working in San Francisco, we didn't want to bring all the dirt back to dump it in the dumpster after we were done testing. So I would do these in the field and leave the dirt out there. Unconfined compression, if you're using it for soil, you extrude a soil sample tube, and it's flat on the top and flat on the bottom, and you put it into this device. The pressure is recorded with this black needle, but the red needle rides on top of the black needle, so you don't have to be watching it all the time. And the red needle sticks at the highest point. And you can see how much shrinkage there was in this through pressure at the failure point by looking at this measuring stick on the side. And in this soil sample, if you look really closely, you can see the classic 45-degree angle shear failure in the soil. And that point is important for the engineers for their design. Now, there's a similar type of test called the point load index, and it's the same sort of device, only instead of having flat surface top and bottom like it does for the soil, it has points on these cones that are holding the rock. So that's why it's called point load. And it's the same sort of thing. I couldn't find a photograph that I liked for this. So you apply pressure, pull down on the handle, apply the pressure. It doesn't have to be core. This is core, but it doesn't have to be core. It can also be any other rock that you choose. And when the rock breaks, you have reached that load for compression. Then there's triaxial compression, and these machines, the engineers won't let the geologists anywhere near them because they're afraid they're going to break them. But this is something where you have compression on triaxial, means 3 axes. So vertical compression, which you are applying, and then the soil sample has got a water bath around it so that it confines it all the way around. Triaxial means 3 axes, so that would be 1 vertical and 2 90-degree axes, but in this case, in real life, it actually has compression all the way around. And so you don't really need to know anything about these really, except for that they're used to determine the shear strength of the soils. I already talked about the LA Rattler test. The soundness test, this is a cementatious test. So you'll notice that the LA Rattler and the soundness are C's. The cementatious test is testing the concrete to see what's going to happen with freeze thaw. And they do this by submerging it repeatedly into a bath of sodium or magnesium sulfate. And they use one or the other of those chemicals because the crystals that form are just like ice crystals. So they don't have to actually freeze it and thaw it. They just submerge it repeatedly and then let it dry out to simulate those ice crystals. Then we have the gradation curve, and this is where you plot the information that came from the sieve analysis. And this is, the sieve numbers are across the top. The actual grain sizes for those sieve numbers are along the bottom. And on one side, it's percent finer by weight, and the other side, it's percent coarser by weight. So you're cumulatively adding or subtracting the weight of each of these as you go down. And if you get a curve that looks like the one that's highlighted right now, then that is well graded, meaning that there is a little bit of everything there. Well graded, again, is poorly sorted. It's opposite. So this would be something like an alluvium, where there's a little bit of everything. Then we have a couple of other ones here that are these nearly vertical ones that I've just added the highlight to. And those are poorly graded, well sorted. And those have almost probably 80% of this material falls within 2 sieve sizes. These are going to be things like sand dunes, beaches, loose deposits, windblown silt is what that is, pea gravel deposits. So most of the material is within that grain size, those 2 grain sizes on the sieves. The only difference between these two is that one on the right is much finer grained than the one on the left. Then we have this other one that's called a gap graded or skip graded. And most of the time, this has a bench in the middle. And most of the time, this is something that is sold to you as a prescription that you take to a quarry and say, I need some of this. And then they'll come with 2 front end loader or 3 front end loaders of this stuff that's between the 3 and 6 sieve sizes. And then they'll go and get 2 front end loaders of the stuff that's between the number 40 sieve and the number 70 sieve or something like that. And they will dump it into your truck, and then you mix it up on the job site. These do occur in nature, particularly in areas where you would have flash flooding, for example, because the major rivers will always carry, this is in the Southwest, will always carry a certain amount of suspended and sediment bedload sediments that will deposit beaches on the sides of the river. And then when you have flash floods in the side canyons coming down the sides and dumping into the river, when the water slows when it enters the main river, then it dumps out all this other stuff that has a lot of other grain sizes in it that are much coarser. So you can see these in nature, but they're not as common as getting it as a prescription from a quarry. Density testing. If you've ever done these, they're pretty boring. As a young geologist, I had to do a bunch of these. And at the time that I started, what this is a way to evaluate how much compaction has been undertaken to achieve a compaction that matches the requirement for the particular job, the specifications for the job. So you will do a compaction curve, or the engineers will do a compaction curve. Sometimes you do too if the engineers are too busy in the lab. And that gives you a specific value for the maximum dry density. And then you compare what the compactive effort is to that maximum dry density. And that will give you a percent compaction. And whatever your requirements are vary depending on what the project is. If it's a nuclear power plant, obviously it's going to have a higher compaction requirement than it would for a landscaping area in a housing development, or a parking area in a strip mall or something like that. So this testing used to only be done with a sand cone, which is what I had to do when I got stuck with this job, where you dig a hole and you keep the dirt and you weigh it. And then to figure out the volume of the hole, you put the sand cone on top of it, and the sand is a standard sand that always gives you the same response in terms of the volume, not the same answer, but the volume of the cone is the same and the fall is the same. So you will calculate the volume based on how much sand gets filled in here. And then you dry the sand out, not the sand, the soil that you dug out after figuring out what it weighs when it's wet. And then, so you weigh it and you dry it and you weigh it again, and that gives you the moisture content. So you can figure out what the percentage of moisture is, and you can remove that moisture from the sample that you have in terms of calculations, and figure out what the pounds per cubic foot of that material that was dug out. Takes a long time. You could probably do 12 of these on a good day, assuming the contractors weren't harassing you all the time. And then about the time that I was experienced enough as a geologist that I didn't get these jobs anymore, they developed this thing called a nuclear density gauge. And what you do is you take the hammer with a big rod and you pound the rod down into the ground to make a hole, and then you push this probe, which has a radioactive source at the bottom of it. It's shielded when it's inside the machine, and then you push that down into the hole. And that then has detectors that will calculate the density. And the original ones would only calculate the density and not the moisture content, but apparently they have some new ones that do all the work for you. But this is kind of a little bit of a black box. Is it working or is it not working? Is it working the way it's supposed to? So if you're using a nuclear density gauge on a regular basis, you probably should be doing a sand cone density every so often to check to make sure that the nuclear density gauge is accurate. Then we have some plasticity tests. This is toughness test. It's just making worms. It's the same, it's the formal name for making worms. And if the material is not very plastic, your worm falls apart very quickly. But if it is highly plastic, you can make that worm roll out for hours and it won't break up. So this is relative plasticity. So these are field plasticity tests. Then another thing you can do is you can make a little pad of soil and you can dry it out. And if it breaks apart easily, then it's not very plastic. But if it's hard to break it, then it is a high plastic material. And the last one that you can do is called the dilatancy test. This is basically a liquefaction test. You put the pad of soil in the palm of your hand, and then you hit your hand with your other hand to jar it. And if it liquefies and you get a glassy surface like you see in this picture, that's a low plastic material. If it's a high plastic material, it holds tight to that water and the water does not surface. So that's going to be more plastic than the stuff that comes to the surface more easily. Okay, come on, go. All right, the engineers who are way over on one hand and understand nothing but numbers need to have a translation from the geologists who are way over on the other hand and talking nothing but concepts. And so one way we do this is that we will give them RQD values for rock. RQD is rock quality designation. And this is where we turn a box of rocks into numbers so the engineers can understand what's going on. And there's a lot of other important information that they get from this, but it seems to me that the only thing that they're really concerned with is the RQD. So how do we come up with RQD? Well, what we do is we take the core run and we look at all of the pieces that are twice the diameter. Now, most of the time we do 2-inch core. So that's the N series cores, NX, NQ, and W. And those are just different designations for different types of core barrels, but they all give out the 2-inch core. So for 2 inches of core, we need, for 2-inch diameter core, we need 4 inches or longer. So we tally up all the pieces that are 4 inches or longer for 2-inch core, 6 inches or longer for 3-inch core. A box of 3-inch core is so heavy that you can hardly even pick up one end, let alone the whole thing. That's probably why they do 2-inch core. Anyway, and you compare that to the total core run. You can't compare it only to the recovery, because if you compare the good rock out of the core run to what you get back, you're going to have an artificially inflated RQD. And that means something bad's going to happen during construction or after the building's built, or somebody's going to get hurt because of the values not being accurate. So let's take a look at this core run and see what we see. The first one here, we've got pretty good recovery. We're only missing about 6 inches. So there's a little bit missing here, and these are 2x2 blocks, so which actually means 1 3/4. But anyway, so we're missing a few inches. That's not bad. So recovery is pretty good. But when we look for 4-inch pieces, I think that the first one that I come to is this one here. Then we've got another one here. And that's about it. Everything else is all broken. So 8 inches out of 5 feet is pretty poor RQD. Then we look at the next one. Okay, our recovery here was crap. We're missing probably 1.5 feet here, but what we get is good. This is one long piece. Here's another long piece. Here's another long piece. Here's another long piece. So if you only compared these long pieces to what you got, you'd think that it would be excellent RQD, 90%. But instead, we're missing 20% of that. So we're down in the fair category, 50 to 75% RQD. So you can see that it matters. The stuff that's gone is the stuff that's crappy. It's ground up easily. It washes out. There's no substance to it. So those are the numbers that the engineers want to see. A couple of other tests. The inclinometer is used to monitor slope movements. You take this special casing that has these grooves in it every 90 degrees. You drill a hole in a landslide, for example, and you insert this casing into the hole, and you dump pea gravel around it to backfill around it to hold it in place. Then the device with the little wheels on it goes into those grooves, and you send it down to the bottom, read it coming back up, turn it 90 degrees, send it down to the bottom, read it coming back up. You got a baseline measurement. If it rains a whole lot, then you'll go back and do it again. If you have an earthquake, you'll go back and do it again and see if the orientation of that has moved, which means that the slide has moved. You can also use these in a couple of other instances. I used to work in a mine for a summer when I was in college as an intern, and we would go down underground once a week to map the tunnels that they had just opened up. And the engineers had little cubbies installed in the wall of the tunnel, and they would insert this device that had both an extensometer, which is measuring pressure from vertically, and an inclinometer component to it, which would measure it not being straight up and down any longer. And that would tell them we were about 6,000 feet down. So rock with that much overburden pressure has a little bit of a very slow liquid character. And so they wanted to monitor that so that they would make sure that the miners were safe. They always made a really big deal about number of safety days that they had there. So that can be used to measure. The extensometer measured the vertical pressures, and the inclinometer measured the shearing pressures, because the rock would change orientation a little bit when it was flowing, if you will, into the open spaces of the tunnels. It could also be used on the face of a dam if you saw that there was some bulging or something in a dam face, which probably means that there's going to be a failure problem, then you might want to install one of these on the face of the dam and monitor it to see if and how much that was happening. Manometer, this is the liquid column instrument. There was some heavy rains in the Bay Area, which reactivated a bunch of old landslides that houses were built on. And so I did a lot of these topographic maps of the floors of these houses after this winter, because people couldn't open their doors and windows anymore. So they'd call us out to find out what was going on. And indeed, the landslide was moving, but the engineers needed some information for the floor levels to be able to level up the floors through piers or jacking or something with the soil injection grouting. So this was, I didn't have a picture of this, but this is a reservoir that I would put somewhere on the first floor, and I would put a grid pattern of tape, masking tape on the floor, and then out of the bottom of this reservoir there is a tube, and the water in the tube equalizes with the water in the reservoir. And so I taped that tube to a yardstick, and then I would read every square and create a topographic map of the floor. And if the water went higher on the yardstick, that meant that the floor was down. If the water went lower on the yardstick, then that meant there was a high spot in the floor. And that way the engineers could work with that. A data logger measures temperature, pressure, and humidity. And if any of these things can help with anything else that you're doing, this can be run concurrently with the other tests that you're running. Engineers talk about slopes in terms of percent grade. And they also talk about slopes in terms of a horizontal to vertical ratio. And so most plans for fill slopes and cut slopes and things say something like 2-to-1 or 3-to-1 or something like that. And 2-to-1, what that means is that you can draw 2 squares over and 1 square up, connect the 2 endpoints. That's your 2-to-1 slope. In my fan here, that slope is here. Anything flatter than that, the engineers can handle on their own. Anything steeper than that, the geologist should be involved. So if you see a ratio, it's probably horizontal to vertical. But if it's not, if it's vertical to horizontal, it would be this slope. 2-to-1 vertical to horizontal. This is actually 1-to-2. I would call that 1/2-to-1. But that slope is pretty steep, and the engineering geologist should be involved here for something that is that steep. So 2-to-1 vertical to horizontal is very different than 2-to-1 horizontal to vertical. So if they have a ratio, make sure that you know what they're talking about. If they don't say anything about it, I would assume that it's horizontal to vertical, because that's how the engineers talk. Okay, so percent grade. Engineer speak. It's the rise over the run. What is that to you guys in hydro? That's the gradient, except for that you guys use a decimal number and the engineers use percent. So you just move your decimal place over 2 places, and that gives you your percentage. So, or if you have a percent grade, you move it over 2 places and it gives you your gradient. So just be aware of that, and that kind of translates engineering geology to hydrogeology for you. And then as far as slope angles go, forget it. Don't memorize this. Don't even look at this column in the table, because they will often have a question saying, what's the slope of a 5-to-1 slope or something like that? So you draw your 5 horizontal line, 1 vertical line, connect the 2 endpoints, put your protractor on it, and you're done in 17 seconds. And you don't have to memorize anything. So I would do it this way as opposed to looking at the slope angle or memorizing the slope angles for these, because it's way faster and uses much less brain power to just draw out 5-to-1. And they will have graph paper in the back of the test booklet that you can do this on, but you don't need graph paper to do this. You just need to be able to do a right angle. So 5 inches over, 1 inch up, and connect the two endpoints. And you're done. Okay, they've increased the number of questions on landslides because landslides occur in more than just California, Oregon, and Washington. A lot of other states get landslides too. So they have finally realized that. And you'd think that they would know this because North Carolina is in the Appalachians and they've got mountains and they get landslides. So it just took them a while to catch on. You should know the names of the features and what they look like. So this block diagram from the USGS is helpful here. We have the headscarp, which is this section up here. Some people call that a crown. Main scarp. The materials move down on the slide plane or surface of rupture, which is between the material that hasn't moved and the material that has moved. And then the part that rides up over on top of the undisturbed ground is called the toe. The base of the slide is the toe. And the terrain is all humpy, lumpy, irregular, cracked up, little ridges, little bumps. That's called hummocky terrain. That's kind of a funny term, but it's the technical term for that bumpy stuff. And you can see that bumpy stuff really clearly in this photograph we have here. This is a single from a stereo pair from Ray. This is a slide that's in Colorado. I don't know where it is. He doesn't specify, and I haven't seen it, but this is more than a mile across. So it's a great big slide. And this humpy, lumpy, hummocky terrain is pretty clearly marked here. And this is probably an active slide. A couple reasons. One is the stream is here, dumping water into the slide every time it rains, which is few and far between, except this year we've gotten quite a bit. And that's adding water to the slide, and I'll talk more about this in a minute, but you can see everything above this red line that I've put here. This is all smooth. It's not hummocky. It's not humpy lumpy. So this is our headscarp right here. And this is the slide mass. It comes up here and goes across over this way as well. The area that gives me a pretty good indication that this is an active slide is right here, where they have probably just done another road repair. This road probably used to be straighter along here, because the biggest indent in the road is where the stream is dumping water into the slide mass. And this area that I've this irregular area that I've outlined here, this is an area where newly exposed ground is showing up at the surface. And I know that that's the case because it's not had any time to get any iron staining or manganese staining to darken it up. And there's no plants growing on it yet to darken it up. So this is probably an active slide. The toe of the slide is down here. There's a stream at the bottom, which probably removes the material that falls into it, keeping this slide mass active. Monitoring landslide activity. I talked about putting in piezometers or inclinometers casing to be able to monitor it. Another thing that I used to do was take a nice little Sharpie, and everything that I was doing was related to buildings, mostly houses in the hills that were failing because of slides moving. So I'd go out and find the foundation cracks that looked like they were structural cracks and not shrinkage cracks, and I would draw a line across it. And I'd label it so I knew which crack I was monitoring. And then I would measure the gap. in that, and that would tell me how active it was, and I would keep going through the repeatedly go back through these houses and mark those. Your job as a licensed geologist is to protect the public health, safety, and welfare. And that doesn't mean that you have to tell them that it's time to evacuate, but you need to tell somebody to tell them that it's time to evacuate. And that's usually the local jurisdiction that does that. So if you see those cracks starting to open up more quickly, then that means that the slide is moving more rapidly, and you don't want people to be in that house when it collapses because of the failure. So you would tell the local jurisdiction and they would talk to them about evacuating. Then we have slope failure prevention and mitigation. And this is rock slope stabilization mitigation. This is a new table in the study manual. And I'm not going to go into these, but you might want to take a look at the descriptions for some of these means of stabilizing the rocks. We've had a lot of problems here in Colorado in the recent years along I-70 because the slopes are quite steep next to the highway, and they have a number of slope stabilization methods there, but it doesn't stop whole great big pieces from falling off. So the catch fences will stop the little rocks, but it doesn't stop the big slabs. And then we've had this summer, because of the massive fires that we had last year, we've had a lot of mudslide problems onto I-70 and Glenwood Canyon, which has closed the highway down for weeks at a time in some cases. So having a major interstate shut down through Colorado is problematic. But take a look at these and see. There are some pictures in this document. It's available online, so you can easily access it. The same with the soil slope. And this publication by Hyland and Bobrowski, it has lots and lots of pictures. So if, as you're looking through the table that's in the study manual, or for those of you that had the older book and are just updating, this would be in the packet of extra material that I sent you. The table would be this. If you don't understand something, there's pictures of before, there's pictures of after, there's pictures for various different types of mitigation methods. So I would definitely take a look at this. It's a circular, it is available online, so you can order it to get a hard copy, but online is just as good and more easily accessible. Factor of safety. This is an analysis of the risk. So these are used for landslides, and what you do is you add up all the resisting forces and you divide it by all of the driving forces. If the resisting forces are a bigger number, so your number is bigger than 1, then you aren't going to have any problems. But if your driving forces become equal to or more than the resisting forces, so 1 or less, your factor of safety is 1 or less, then you're going to have a problem. So the resisting forces are things like cohesive soils. They're going to hold together better than non-cohesive. Deep-rooted plants are going to tie the soil material together, whereas shallow-rooted plants won't. Some shallow-rooted plants, like pine trees, add a lot of weight to the soil, but their roots are so shallow that they aren't going to tie things together while they're adding weight. So they're a driving force. If you have more weight on the lower part of the toe, it stabilizes it. If you have more weight on the upper part of the slopes, then it is going to be destabilizing it. High coefficient of friction will tie it together better. The risk of seismic shaking, if you have very little risk of seismic shaking, like in Florida, for example, And Patty will talk about seismicity in a little bit here, but every state almost, there's only 2 or 3 that don't have problems with this to some degree. But Florida doesn't have any hillsides either, so they don't have to worry about it because they don't have any steep slopes. So lower risk of seismic shaking is going to be resisting West Coast states and other areas where we have a lot of seismicity is going to be a driving force. Flatter slopes obviously are less likely to fail than steep slopes. Short slopes, if they're just little, they aren't going to be as likely to slide as long slopes. And then there's water. Water is always a problem. Water does 2 things. It adds a lot of weight. Water's heavy. And it also lubricates the grains so that they will slide past one another easier. So the first thing that you want to do is get the water out of there. And you can see in even places where they won't talk about landslides very much, they will put horizontal drains in road cuts. And those horizontal drains are perforated pipe that are designed to drain the water out of the ground underneath a potentially unstable slope. And that will reduce the risk of having that slope fail. Now, those always have to be maintained, and what tends to happen is that they install them and think they're good forever, but they don't. They have to be maintained. They have to be cleaned out so that they will continue to work. Okay, next. Markland wedge analysis. This is a StereoNet. And if you listened to the link that we sent you, you will know that you can't bring a StereoNet in. I don't understand that at all, because the engineers get to bring in anything that they want to take the test. But we aren't. So we can't bring in a StereoNet, and if they provide you with one, then it won't be usable because you don't have a pin and you don't have an overlay to draw on. So what they tend to do is give you a completed StereoNet and then ask you what the deal is with it. Is this something that we need to take into consideration? So here's the completed StereoNet. So let's take a look at what all these lines mean. On a StereoNet, a plane becomes a line or an arc, and a line becomes a point. So what do these lines mean? All right, well, here's our StereoNet. And if we think about a StereoNet being a bowl, it's the bottom half of a sphere for the purposes of this exam. So the StereoNet is a bowl that's sitting on our desk. If we take a piece of paper and we lay it on top of that bowl, where's it going to touch the bowl? That piece of paper would be representative of a horizontal plane. It's going to touch the bowl all the way around the outside edge. So that outside edge, this is a line that starts and stops at the same point. So for a horizontal bed, this is what it's going to look like in a StereoNet. If we cut the corners off and make a half round on the bottom of our paper, then we can stand that up vertically in our StereoNet, and it will be a line that is going through the center of the StereoNet. And it doesn't matter what orientation that line has, that vertical bed is always going to be a line straight through the center of the StereoNet. Okay, now not everything is vertical or horizontal. So how do we plot stuff that's not? Well, if we take our little piece of paper and we make it horizontal again, if we have a slight dip, 10 degrees say, that's 10 degrees in from the outside edge. If it's dipping to the east, you measure on the east axis. If it's dipping to the west, you would measure it on the west axis. So this is 10 degrees in And it's a very curvy line that's very close to the outside edge. As it gets steeper, it moves in. And I'm going in 10-degree increments, which are the heavy lines in the StereoNet. 30 degrees, it's starting to get straighter, 40 straighter, 50 straighter still. And as we move away, it gets steeper and steeper. And then we eventually will get to 90 degrees, which is vertical. So those lines will be, the curvature of those lines will give you a kind of a little bit of an indication as to how steep it is, what the dip in general is. Okay, now not all strikes are north-south. Everything I've done so far is for north-south, but not all are north-south. So what we want to do is we'll go back to our StereoNet again, and our cut slope, which was the blue line in our diagram, is striking north 42 west. So I measure from north to 42 west. Then I rotate my overlay up to the top. And then my dip is going to be 45 degrees northeast. So since it's east, I'm going to measure in on the east side. If it was southwest, then I would be measuring in on the west side. So I'll measure in 45 degrees, 10, 20, 30, 45. And draw in the great circle. And then I rotate that back to the original position of strike. And there's my cut slope. So it's not really very difficult to visualize. And what I will usually do is I'll use my hand as kind of a substitute for the piece of paper, and I will turn it to north 42 west, and then I'll dip it to the northeast, and that kind of shows me the quadrant, at least, that my line is going to be in. All right, one other piece, and that is the phi angle. That's the angle of internal friction. And basically anything that is flatter than our phi angle will always be stable no matter what, all the time, all the time, all the time. So how do I draw that? Well, in this case, it's 12 degrees. So I will put my pencil lead at 12 degrees on the east axis because I'm right-handed. If you're left-handed, it's easier to do it from the west axis. And then I just rotate my overlay underneath my pencil, holding my pencil on the east axis. And what I get is a circle, and it is 12 degrees in on the east, it's 12 degrees in on the south, it's 12 degrees in on the west, and it's 12 degrees in on the north. So that is my angle of internal friction. So everything that is between the purple line and the outside of the circle is going to be stable no matter what. Anything inside might be stable, might not be stable. So going back to our problem, the blue line is our cut slope. The purple line is our angle of internal friction. And the red and green lines are joint sets. And what we're trying to do with the Markland wedge analysis is to figure out whether the big blocks of rocks are going to fall down and smush the cars. So what we're looking at is the intersection of these joints, which is right where the planes intersect on our StereoNet. And two conditions have to exist at the same time. First of all, that intersection has to be showing up outside the cut slope. So you see it in the cut slope. If it's not outside the cut slope, if it's back behind the cut slope, it's dipping into the hill and you're not going to have a problem with it. So we just want to make sure that this is not outside the cut slope or showing up in the cut slope. That's called daylighting. Then the other thing is we want to see if that intersection is steeper than the angle of internal friction. So if this intersection was out here somewhere, then it would be stable, because everything flatter than the angle of internal friction is always going to be stable. So if it's out here, it's going to be stable. So basically, if we shade in the space between the cut slope and the angle of internal friction, if our intersection is anywhere inside this crescent moon, you're going to have failure eventually, if not immediately. And you don't want those to smush the cars. Okay, so there we are. Now what do? We have a problem. Well, it can be a couple of different solutions. One is that you can change the orientation of the road. What you want to do is you want to get this intersection somewhere back here behind your cut slope, or out here in the angle of internal friction less than the angle of internal friction. This is harder to do, but this is pretty easy to do. So what we'll do is we can move the road. So we're changing the location of the road a little bit so that it changes the dynamic of the hillside with that joint set. So here's our new road. We've moved it over. And now here's my crescent moon. So that slope, the intersection of that slope is behind my cut slope, so it's okay. The other thing that we can do is we can flatten it out. So here's our original slope. This is 25 degrees. So if we make this flatter, this is 45 right now, but if we make this flatter than 25 degrees, meaning we cut the slope back a little bit farther, a little bit gentler slope, then there's our crescent moon. Then that is behind the slope also. It's not daylighting in the slope, so it's going to be stable. So there is things that you can do. You could also rock bolt if the rock was okay to bolt. Some rock is, some rock isn't. And that's just taking rock bolts with big steel plates and just screwing them into the hillside so that they don't fall down. Sometimes these will eventually fail anyway, but so there's a couple of things that you can do to fix this. Okay, now we have a couple of questions before I go on to dams. One was an anecdote here. Last year, we extracted andesite core in El Paso. The core sections were almost 2 feet long. Very nice samples. A week later, we opened the boxes and the rock had crumbled almost completely. There were very few pieces long enough to do tests on that were left. We assumed it was due to depressurization, but we never had seen the rock do that before, especially not andesite. Would the test results represent the actual condition of the rock if the in situ rock would not be exhumed? Well, you'd have to do the tests right away to be representative of the in situ rock, because that was the rock that was done right away. Once it's exhumed, maybe it's drying out, and so it's not holding itself together when it's dry, whereas in the hillside it might have been wet, which is the same sort of thing with soil, because the dried out soil acts very differently than the wet soils do. Question about the direction of the drains on slopes. They describe the type of material and angle. Can't remember the details, but the question was, in which direction would the drains work best, perpendicular versus parallel to the slope? Somewhere in the middle at the foot of the slope, something along those lines. Okay, so if you're putting drains in, you have to have some gradient to them, otherwise they won't drain. And depending on what the situation is, if you're putting in a fill slope or a cut slope, then you need to bench them. If you are putting those in and you put vertical drains, then it's just going to create an erosion channel. And that erosion channel will eat away at the hillside. So you put benches in, and those benches have to have a constant grade so that the water will flow down them. But then they carry the water off to the side of the hillside and then get carried away by pipes usually. And those specifications are by state, and those the Unified Building Code is where you're going to get details on the installation of drains. But most of the time with landslide repairs, for example, they will put in drainage underneath the repair so that the water doesn't get up into the repair and cause the repair to fail. And then those get drained out to a sub-drain that goes into the storm drain system. But those are usually relatively horizontal drains with a, I don't know, 1%, 2% grade, depending on the specifications, so that the water continues to flow without flowing so fast that it erodes away the hillside. The question, will they have StereoNet questions if we can't bring them in? They will have StereoNet questions in that they will give you a StereoNet that is complete and ask you a question about it, similar to this question that we have laid out here in your, I think it's in the course notes. Let me see here. Yeah, this question is in the course notes on page 16. So the StereoNet that I drew is on page 17 in the practice questions. And what they'll do is they'll give you a completed StereoNet and say, okay, so is this going to fail? Or what are you seeing in this StereoNet? What's the strike and dip of the bed, approximately? And you can pretty much interpret that from the orientation of your lines. So you may not have a StereoNet. They might just give you something. Let me go back to the incompleted one. Come on. Okay. Oops. Okay, so give you something like this and say, what's the strike and dip of the blue bed? And then they'll give you north 42 west, north 42 east, south 42 west. We only do strikes in the north quadrants, but they can ask you that. And then they would say dipping to the southwest, and if that were the case, then the line would be on the other side. Dipping to the northeast, the line's on the upper side, the way it is drawn here. So they can ask you strike and dip from StereoNets. They can ask you like a Markland wedge analysis question from StereoNets. They will provide you with a completed StereoNet and ask you questions. And the answers will be orders of magnitude. So they would say, okay, so north 42 west, 45 northeast. That's the answer. But they could say north 42 west, 10 degrees northeast, in which case this arc would be way out towards the edge of your StereoNet, and it's not there. So they can ask you generalized questions even without StereoNets being able to be brought in. I don't understand that, because it doesn't really make any sense that the engineers can take their stuff in, but the geologists can't. They're not going to ask you complicated questions about StereoNets because you're not allowed to use them. So you don't need to worry about fold axes and unfolding beds and all that stuff. Most of the stuff that we included for that type of analysis, it's fun to do on the StereoNet, but those are going to be in Appendix 2 and not in Chapter 2. So it's just the basics. Determining apparent dip from true strike and dip, and you'll be able to do that. If you work with it a little bit with some of the basics, you'll be able to get a handle on what that would be. But they're not going to ask more than one question about StereoNets. So everybody freaks out when I start talking about StereoNets, and I tried to make it as simple as I possibly could to be able to figure that out. But anyway, I wouldn't worry about it too much. I have done sort of the kind of thing that you need to be able to understand for the exam. Okay. Parts of a dam. You need to know, as far as dams go, you need to know what these are, what the names of these things are. So I would take a look at this so you're familiar with the terms. You want to also, when you're looking at putting a dam in, you need to know what the impact of the geologic conditions on the dam site is going to be. And this is not just the dam embankment area, this is around the entire reservoir. And some of these don't necessarily have to do with failure of the dam itself, but failure of the reservoir. So you want to look at where there is landslide potential, not just in the dam embankment area, but around the whole periphery of where the water is going to be. Faults, do we have any faults that are going to impact this? What about seismicity? What's going to happen when we have an earthquake and this dam is there? It's going to develop a sesh. What's a sesh? A sesh is the water sloshing back and forth because of the earthquake waves. And you can kind of liken it to a 2-year-old in the bathtub that's discovered that the bottom is slippery, and it's fun to make the water slosh up on the side, and eventually it goes over the top and onto the floor, and lots of giggles happen, and then it drips through the ceiling downstairs to the dining room. But the little kid is like the earthquake waves, and the sesh is the water sloshing within it. And seshes can cause a dam failure by overtopping the dam and eroding the downstream embankment, which is supporting the dam. So you don't want to have that kind of thing happen, or at least have some sort of mitigation for that. And I don't know what that would be, but recognizing that that's a possibility. Deleterious materials, that means bad stuff. And I'll talk about some of those as we go along. What's the underlying geology? Is there anything that's going to cause problems? We have to know where aggregate sources are. If you're building a concrete dam, you have to have non-reactive aggregate to build your dam with. If you are building a earth-fill dam, you have to have a lot of different kinds of material. You got to have enough clay to make up the clay core, which is the impervious zone in the dam, so the water just doesn't flow through it. You've got to have other earth and rock materials to support that clay cores for the upstream and downstream embankment materials. You've got to have rock, drain rock, that's all the same size to make the inclined drains and the blanket drains and the toe drains to keep the water out of the downstream embankment materials. You need to have probably some riprap surface here, unless it's a dam that nobody can go on the water for it. Some water systems won't allow you to go onto the water in their reservoirs. Others do. And if you are driving around on jet skis, it's going to make big waves, and it's going to erode the upstream embankment and may cause the dam to fail into the reservoir. So you need to know where those sources are. And a lot of what the engineering geologist does at the beginning is finds aggregate sources for the various materials you have within close transportation distance to be able to build the dam that they want to build. Then there's dam monitoring. I already talked about dam monitoring with the inclinometer to see if there's any distress in the downstream embankment materials. But also, one thing that's really important is knowing where this phreatic line is. So this red line I've just drawn here, this is the level of the water within the dam embankment itself in this earth-fill dam. And that phreatic line cannot intersect the downstream embankment, because if it does, it will cause the kind of piping that they had in the Teton Dam that destroyed the dam in one day. And so you want to monitor this water level. So you install a piezometer in the axis of the dam. Then I would probably put another one just a little bit downstream to make sure that that is tailing off properly. And I might even be inclined to put a third one in to make sure that this one is dry. If this one's got water in it, we have problems. That dam is going to fail. So put in a couple of piezometers to monitor that. to make sure that that's not going to happen. Now that's why these drain rocks are put in here. Question is asking what the phreatic line can't intersect. This phreatic line has to tail down to the ground surface within the clay core. It cannot intersect the downstream embankment materials. And some dams don't have drain rock in the downstream embankments here. And if that's the case and this enters that, then it's going to cause the downstream embankment to erode away and the dam will lose its support. The drains are here to make sure that this is dry, this downstream earth zone has got to stay dry. Okay, then there's dam siting. I'll just tell you, and you can figure out for yourself what the situation is for each of these. In your study manual, the failure mechanism loading is at the bottom of the page with the diagram. They're reversed. So the dams are on top and the loading system is down below. But each one of these dams is set to fail. So you should, just knowing that, you should look for what could be causing the problem in here. And these are the lithologic symbols for these various materials. Fractures, these are joints, fracture joints, sets. We've got shale here, we've got faulting, fault gouge can be a problem because it's clayey and often swelling material. So just look at these and see what you think for each of these. But these are not good dams, just so you know. So what we want to be looking for is the soundness of the foundation materials. The materials underneath need to be sound enough to support the dam because it's heavy, but it's even doubly heavy by the water, the weight of the water behind it. So you need to know the load-bearing potential and load-bearing capacity. Now, this is especially important for concrete dams because concrete dams, they will fail quickly with very little differential settlement. They'll just crack. Earth-filled dams have a little bit more tolerance, but they will fail as well eventually if there's too much differential settlement. So you need to understand what the load-bearing potential and the load-bearing capacity are of those subsurface materials. How watertight is the foundation of the dam? I already talked about grouting under the reservoir, but if any of these dams have water underneath the dam, it's going to enhance the risk of dam failure. So you want to make sure that all of these materials that are underneath the dam are dry. So you come up with an appropriate grouting plan depending on what materials need to be grouted and what don't. The prolonged exposure of water on foundation materials can be a problem. Slaking is a characteristic where you take a rock, you put it in a pitcher of water, leave it overnight, the next morning you have sand. It is rock that under the presence of water has no structural integrity. So there was a dam built in Southern California. It's called the St. Francis Dam. It was built in 1928. I mean, it was it was completed in 1928, and the engineer Mulholland, who has a name in Los Angeles named after him, built this dam. This is a guy who got his engineering degree because he had built a bunch of dams, not because he had taken any engineering classes. Anyway, this dam failed overnight and killed more than 400 people downstream, a lot of whom were never found. So it's up in the hills north of Los Angeles, and it flooded all the way down to the Pacific Ocean. So one of the abutments was built in slaking material. So when the reservoir filled up, it saturated that rock that slaked, and provided no support for the dam. The other abutment was in an old landslide, an ancient landslide that hadn't moved in a long time. And what happens when you fill the water up behind a reservoir, the groundwater in the surrounding hillsides rises to meet it. And so the groundwater rose up and re-lubricated the slide plane. And so on the same night that the slaking failure happened, that landslide moved. So both abutments of the dam were destroyed in the same night, which is what made this be such a giant disaster for the people that were downstream. There was a lot of farmers down there. And I read a book that was pretty interesting. They valued the people's dead bodies based on race, basically, because they didn't give much money for the people that were working the farms, but they gave a lot of money to the farm owners. So anyway, I won't dwell on that, but it was a major disaster. Another situation here, and these are both under this earth movement potential at the dam site. The Vajont Dam in Italy, when they filled that up, it was a very narrow dam closing off a very narrow canyon. And when the water filled up behind it, it caused the whole mountainside on one side of the reservoir to fail. And all of the water in the reservoir was displaced by this failed material. And it went over the top of the dam. The dam still held. And about 1,900 people downstream were killed. This was in 1963. So even more recently, people hadn't learned about this, but that was in Italy, not here. And then seismic loading potential. So you'll see when Patty talks about this, I'm not going to really talk about this too much, but earthquakes and seiches can be problems. And Patty will show you that more of the US has seismic loading potential than you guys actually think. Types of dams. By purpose, a storage dam holds water. This is Shasta Dam in California. I'm pretty certain that the water levels are way down from this right now. But storage dams store water during the rainy season and from snowmelt, and then it's used for drinking and for irrigation and all that sort of stuff. So it is drawn down during the non-rainy season and it builds up during the rainy season. Detention dams. These are for flood control. So this dam was built to keep this valley from flooding when it rained really hard. And so what they'll do is they'll stop the water and then they'll let it out so that we have an open space here again to stop the next storm. So as long as the storms aren't too long and prolonged and piled up on top of one another, then these dams will work to protect the people from flooding. Then we have diversion dams, and these are used to divert water into canals or irrigation dishes or aqueducts to carry water away from Northern California to Southern California. Southern California gets the majority of the water from Northern California, and so this water is pulled out and diverted down to Southern California. That's just an example. But they sometimes don't even dam the whole thing. They let a lot of water through so that they only divert what they need. Then we have debris dams. These, when it rains a lot and the water on the hillsides carries debris down into the major rivers, then this debris can create its own dam, which can be really dangerous. And so what they'll do is they'll put in a debris dam, which is stopping all this crud from going downriver and creating its own dam, which is unengineered, which can fail at any time because there's no engineering design there. But then they'll skim this all off the top to make this safer. Then we have cofferdams, and these are just temporary dams. In this case, this is one that has been put in. These are sheet pile dam here, and then they pump the water out so that they could build a footing for a new bridge across this reservoir. And then once the footing is built, then they'll remove all their equipment and start pulling the sheet pile, and it will fill in that space where the dam will, or the bridge support will then be just surrounded by water. So that's called a cofferdam. Structure type. Gravity dams, the Grand Coulee Dam is a hydroelectric dam up in the Pacific Northwest, and it's called a gravity dam because the heaviest part is at the bottom, so it's got a fat bottom, and that will give it its stability. The arch dams, the most famous one is the Hoover Dam, and this is nearly empty right now as well, but this is a arch dam that arches upstream. It's notched into the hillside so that when the pressure of the water behind it pushes on this eggshell of a dam, it will spread the pressure out into the hillside in both of these notches. We have buttress dams. These are concrete buttresses, but what we have is a slab that is supported by buttresses. So our concrete buttresses, you can also have timber buttresses or steel buttresses that can support that slab as well. And then there's the earth-filled dams, and these are pretty wide at the bottom. These tend to be much bigger, bigger footprint on the ground than the concrete dams are. Tunnels. Know the names of the parts of the tunnel, and this is for economic as well as for engineering. So take a look at those so that you're familiar with those terms. You want to know what the impact of the geologic conditions are, and these are all the same kind of conditions, except for we don't have to worry about seiches for tunnels usually. Excavation methods is what the engineers are recommending for these, and this is either tunnel boring machines or drill and blast. And drill and blast is in hard rock. Don't usually use that in soft rock because soft rock can just be excavated, or earth can just be excavated. But the thing about tunnel boring machines is that nobody wants blasting underneath their houses. So for all of the urban type projects, you have to have a tunnel boring machine, because the tunnel boring machine will eat its way through without what the people are concerned with, shaking the ground. If you're a mile down, you can't feel it at the surface, but they swear they can. So soft rock tunnel boring machines won't tunnel hard rock, and hard rock tunnel boring machines won't tunnel soft rock. And so as engineering geologists, you want to give them an idea of what it is that they are working with before they start in with this. Because you want to use the least expensive equipment that you can, but if you start out with a soft rock tunnel boring machine and hit something that's too hard to go through it, if there's only 10 feet of it, one small blast would take care of it, and then you just keep going with a soft rock tunnel boring machine. But if you're going to be going through 100 feet of it, then you can't do that. So some of this is political, obviously. But when you are drilling with this, we have a cutting face here, and the cutting face is different for soft rock versus hard rock. Then we have the machine shield, which cannot be taken out. It can only move forward, because behind that we have these segmented sections and for the workings of the mine tunnel. And then behind that we have sections that are shotcreted or concreted in to keep the tunnel supported while people are working in there. And you can't back this out. So in order to change from a hard rock to a soft rock, you would have to take all this machinery out, take the cutting face off, and then put a soft rock tunnel boring machine in through the center and telescope down. And so if you have to do that too many times, your hole ends up being too small at the other end. They do have some much more expensive machines now that are able to take on both hard rock and soft rock. And if you have a lot of variability, that's going to be the least expensive way to do it. And then there's tunnel siting. One thing we have to worry about is faults. And it doesn't matter if it's active or inactive, you still have to worry about it. Active faults for obvious reasons, but inactive faults can cause problems as well. And that is because the inactive faults can make if it's a gougy zone, then it can have a water barrier. So one side, the water is going to be very high, and the other side, it's going to be very low. If you go from the low to the high, all of a sudden you're going to have Niagara Falls running through your tunnel, and it can wash out all the people and all the equipment and be quite dangerous. So you need to know about that ahead of time. If it is hard rock sometimes just breaks up into bits and it's all fractured up, and that will just cave into your tunnel when you have that kind of a situation. So again, knowing about it so that you can deal with it is going to be important. And the most favorable angle to cross a large fault is not going to be keeping it straight at an angle. So we're in this tunnel for a long distance in the fault zone here. And this is for a fault that is just one single line, and not all of them are. Some of them are fault zones, which would make this even longer. So what you want to do with your tunnel is you're going to take the orientation that you've got, you're going to straighten it out so that it is perpendicular to your fault, so that you are in that fault zone for the shortest possible distance, and then pick back up to your tunnel alignment. Incompetent formations. I have talked about swelling and I've talked about slaking already. So there are three others here that you should be familiar with those terms. Look up their definitions in the study manual. There is a table that is on page 13-5, I believe, that gives you recommended tunnel sets. Now, that is not something that you need to memorize. It's a teaching tool that you should use to get an idea of what kind of work you need to do to address these various risks for these incompetent formations. So every tunnel is going to be different, and some may have squeezing and swelling, some may have swelling and raveling, some may have running and slaking. And so you want to take a look at that table just to kind of get an idea of what kind of effort is needed. High groundwater is a problem. Working in high head conditions is difficult. If you have high groundwater, then you have to freeze the ground or work in a compressed air environment for the new part of the tunneling before you can get it lined, and that is problematic and very expensive. Worked on a project in Seattle that they first were thinking about doing a effluent transfer system out to the Sound from Renton, which is a town that's south of Seattle. And initially they looked at just doing cut and cover along the Green River to put this tertiary treated water out to the Sound. But there was a bunch of Superfund sites along the river that they would have had to have cleaned up as they went, and they thought that would be too expensive. So I headed up a field investigation for a deep tunnel out to the Sound from Renton, a straight shot, and it was a very short distance and it would be deep, so they thought it would be cheap. But as it turned out, it was glacial till, which was all interconnected, and so the high groundwater was like 400 feet ahead over this tunnel for the entire tunnel alignment, and they decided that that was going to be too expensive, too dangerous to excavate, so they went back to the cleaning up all the Superfund sites because that was going to be easier and cheaper. Just as an example of how to work with this, because the freezing the ground is expensive. And if you only have a small section that you need to freeze because there's only a little bit of high groundwater in a small section, then that would work. That would be an easy and relatively inexpensive solution in the grand scheme of things. But in this case, those high heads were throughout the length of the tunnel alignment, so it was too dangerous. When we have oil and gas deposits, sometimes we can get extreme geothermal heat that can cause problems for construction as well as the equipment. Mines that have sulfide ores will have sulfide gases, which are deadly. Methane gas can be found associated with both landfills or coal beds, and these gases can travel through the soil materials in soil fractures. Also with gas fields with other natural gases can travel through the soil and can accumulate in open spaces. So a project I worked on in Southern California was abandoned. They were going to put a tunnel through along Wilshire Boulevard to actually from downtown a long ways all the way up into Topanga. But that area had, some of those areas along that alignment had gases, and they had an explosion in a station that they had opened up. And when the gas had accumulated enough to be explosive, they had run a test train through it, and it exploded with sparks on the tracks. And so that was abandoned. That project was abandoned. And that was because of the gas traveling through the soils and accumulating. Now, these are things that we can design for. And that is something that we need to worry about ahead of time. That's the engineering geologist's responsibility, to make sure that that information is known ahead of time so that you can design for it. You can build vapor barriers if you are in an area that you know that you have explosive gases, but you don't always. And then bentonite. Bentonite is a swelling material. And so if you are building a tunnel through bentonite, you need to make sure that you have the right tunnel supports to be able to handle that kind of thing. Okay, and my last slide before we take a break here is going to be on radon. And I talked a little bit about this when I was talking about the gamma logs earlier. Uranium is found in most rocks. Light-colored igneous rocks have higher levels than other rocks. So the highest levels of the uranium is going to be in the granites and the rhyolites, light-colored igneous rocks. You also have them in the shales because they accumulate in the non-interconnected pore spaces. Phosphate rocks also. Not so many of those, so you don't worry about those quite as much. And then if any of those rocks are metamorphosed, you will have higher levels of radioactivity in those as well. This uranium decays to make radon gas, and the clay soils will trap radon gas. I have really seriously clay soils here, and everyone in the neighborhood has radon mitigation that's been installed when the houses were built. It's heavier than air, so it accumulates in low spots like basements or subterranean garages or hollows if there's a big problem with it. It's a gas, so it is an inhalant risk. Means that you're going to get lung cancer or other lung issues if you breathe it. It further decays to make daughter products, one of which is polonium, which is also radioactive. So it causes the same health problems that the radon gas would. Okay, so we are going to start in with economic after a 5-minute break. Let us know when you're back. Okay, Patty.